Yes. Welcome, participants. Today is the last interactive session with you on this course, Vibration of Continuous Systems. So I have finished the 12 modules, and you have got the videos already, assignment questions and solutions so far. And I think the last module is currently going on, for which the solution will be posted later on. Now, you know that after the second interactive section, we have mainly covered this 9th, 10th, 11th, 12th, these 4 modules. And 4 modules were on the different topics in the continuous system. And I want to highlight this module, the some special topics or any formulation that is important for any different modules that is frequently used in applications in industrial or this academic research, that I will highlight it. And then I will discuss the questions that is posted for the live session. Especially, I will answer these questions with some equation whenever is needed. Then I will go for answering the questions that you post here during this session. And also, if any explanation is required, I thought that some explanation be given on the answer that I posted in the discussion forum. That was in the text only, but here I may discuss with the equations and formula. So that is the activity here in this today's live session. So now I will start first giving the gist of the modules. You can say the summary of the modules, some important parts or salient part of this module that I will discuss without any derivations. Derivations here I will not do because this will be available in the lectures in detail. Here only I will give the important conclusions, how it is arrived, principles, and how to apply this in practical problems. So many things that are given in this video, some of these things are frequently applied in academic research or in industry. That will be highlighted, and we'll see that how it can be applied to different some problems. So summarize the completed modules that we have already done it, and full question and answer, already available questions from the learners or any new questions that I want. So in the 9th module, I discussed free vibration of rectangular plate and forced vibration of rectangular plate. Only rectangular plate is discussed here, because in case of membrane, I discussed the circular membrane, which are in the polar coordinate form. Similarly, plate is also studied in polar coordinate for circular shape. So that aspect I have not done. In the module 9, I have discussed only vibration of rectangular plate, because rectangular plate is very common in application. Like civil engineering structure, it is a bridge deck which can be modeled as a rectangular plate, or a building slab, or in any other applications, a steel plate is used of different length breadth ratio. So that is there, and we'll see how the vibration characteristics are obtain, especially the model characteristics, frequencies, and mode shapes for the plate. And what is the difference between the mode shape of the plate and mode shape of the beam? That we will also see here. Then I will discuss the force vibration of rectangular plate with the help of model superposition technique. So in case of plate, the governing differential equation is this. D is the flexural rigidity of the plate, which is actually EH cube divided by 12, 1 minus mu square, where mu is the Poisson ratio. And W is the transverse deflection of the plate. QXYT is the distributed load acting on the plate. Here, XY are the spatial coordinates and T is the time. So load depends on the coordinates and time. Rho is the mass per unit area of the plate, and this is the acceleration terms. So here I presented a simply supported plate, which is very common, and it gives a basic understanding of the vibration phenomenon. So rectangular plate I have selected of length A and B, that is aspect ratio A by B. So you can see the boundary condition that I've discussed several times, that at the edges, the deflection and bending moments are 0. So like that, the boundary conditions are written. And there may be other boundary condition, clamped edge, where this edge you can see that y is equal to 0 edge. This edge is y is equal to 0 is fixed. So therefore W is 0 and del W by del y, that is the slope, is also 0. Again at x is equal to A, this W is 0 and del W by del x at x is equal to A is also 0. Similarly, we have the free edge condition, and in the free edge, we have this very special boundary condition, that is 3 boundary condition arises. One is bending moment, twisting moment, and shearing force. But these 2 conditions can be combined. This twisting moment and shearing force can be combined to give a S shear distribution that is known as Kirchhoff's S shear. So that I've discussed in my videos. So now, simply supported plate as a general solution for the boundary value problem. That is, if WXY is the mode shape of the plate, then it has a solution like that. You can see here combination of trigonometrical terms, sine and sine alpha x, sine beta y, like that. Sine alpha x, cos beta y. Different combinations are there of trigonometrical terms as well as hyperbolic terms. Now, there are 8 constants here you are seeing, and also you are noticing that alpha and beta are the 2 parameters. And alpha, beta actually are related to the natural frequency of the system that we have discussed in my module in detail. Constants of integration can be obtained after imposing boundary conditions. So ultimately, for simply supported plate, we get a solution like that. Wxy equal to A1 sine alpha x sine beta y. So if A1 sine alpha x sine beta y is 0, then what it gives? It gives that WAY, that it is also at x is equal to A. It is also simply supported, so W is 0. So it gives this equation. So that indicates that alpha m is equal to m pi. Similarly, for this xb coordinate, that is y is equal to b, it is again simply supported, so that 0 boundary condition gives beta and b equal to n pi. So now, finding the alpha and beta, we can relate this thing to gamma square mn. And gamma square mn contains the frequency, natural frequency omega square. Now you can see that here everything is double subscripted. You can see that this gamma is double subscripted, so this we can write this gamma AMN corresponding to this omega MN. Okay. So because M and N, two integers are here, you can see M and N are two integers. So therefore we can write this gamma MN. So actually it should be written with subscript gamma. So knowing gamma MN from alpha M and beta N, we can now calculate the natural frequency omega MN. Omega Mn is the natural frequency corresponding to Mn modes. So that we have obtained in detail, that shows that these wave numbers, that is M and N, are important. So that appears in the frequency equation, and also the aspect ratio. The length to breadth ratio is also playing an important role. So you can see the natural frequency is pi square m square plus r square n square, pi square into m square plus r square n square, then root over this quantity, where rho a to the power 4 is actually this plate. One a is the length of the plate, and rho is the mass per unit area, where d is the flexural rigidity. So you can see there is some similarity with the beam bending frequency. Beam bending frequency for simply supported beam, we have seen that it is nth frequency, that is n pi whole square into root over ei. So for B, D is now flexural rigidity ei, and rho is say m mass per unit length, and A is L. So you can remember that, recall it, for beam, the natural frequency was Wn equal to n pi square into root over ei by m L to the power 4. So for the plate, this relation is obtained for any mode, that is equal number of waves, half waves that are formed in both the directions, because it is a bidirectional element. So we have to take the number of half waves in both directions. At certain frequency, number of half waves may not be equal in x and y direction. So therefore, this subscript may differ. Now, when the subscripts are equal number of half waves are formed in the plate to get the displaced shape. You can see here the model shape, mode 1, 1 half wave is formed in x and y direction. Similarly, mode 1, 2, you can see mode 1, 2. Mode 2, 2, say mode 2, 2, here. Two half waves are formed. Here one half waves, and also in this longer direction another half waves. So as the number increases, say whether the first subscript say represents the half waves that is formed in the x direction, second subscript form indicates the half wave that is formed in the y direction. So as the subscript number, that is the digit increases, you will get the increase of half waves. Then similar to beam, the orthogonality relationship is also valid. So if W is the mode shape in RMSF mode, and WMN is the mode shape in MN mode, then this orthogonality relationship gives rho WRS into rho Wmn integration dx dy over the domain of the rectangular plate equal to 0. But if r equal to m, s equal to n, this quantity will be non-zero. So now let us obtain the normalized mode shape that we have obtained, and you can see this arbitrary constants associated with the displacement shape in any natural frequency, that is the model frequency, is now obtained if we normalize the mode shape function with respect to mass. So then AMN becomes 2 divided by root rho AB, and you can see the AB is the area of the plate and rho is the mass per unit area. So this becomes MP, the mass of the plate. So in this way, we get the normalized mode shape. So normalized mode shape in the plate we have taken as equal to 2 divided by root over NP sine m pi x by a sine n pi y by b. And remember that it is simply supported condition. Then force vibration analysis, or for analysis of the time response, we discretize the equation of motion as usual using the modal superposition technique that we use the mode summation and then apply the orthogonality condition. Ultimately, we get q double dot mn t plus omega square mn qmn t equal to 0, where the omega mn is the natural frequency and qmn is the generalized coordinates in time. So once we know the qmn and this mode shape function is known, then we can find the displacement at any location xy at any time instant t. So with this principle, the force vibration of a rectangular plate can be studied. And we have considered the damping term here by including the damping force, that is C into C is the damping velocity and this is the velocity. So C is the damping constant. C is the damping constant and del W by del T is the velocity. So C into del W by del T is the damping force. Okay. This is the damping constant that depends on the velocity. Linearly proportional to the damping force is linearly proportional to the velocity. That is the type of damping which is known as viscous damping. But here we also assume that C is proportional to the mass. So assuming the mass proportional damping, that is C equal to 2 rho omega mn xi omega n. That is the mass proportional damping. We now get the decoupled equation of motion in generalized coordinate for damped vibration. So here you can see that q double dot mn plus 2 xi mn omega mn q dot mn plus omega square mn q mn. Force vibration of response of rectangular plate is studied with the help of this general procedure, that is the Duhamel's integral, or any other technique you can use. If it is a harmonic function, we know the standard formula for obtaining the steady state response. And with this, we add the homogeneous solution, that is in free vibration response, and then we get the total response. So you can see here, this is the complete response of the plate. This is homogeneous part. So this part is homogeneous. For any linear system, we obtain that for any linear system, the homogeneous part is added to the particular integral. And this is particular integral. That is due to force vibration. So we get like that, and then if, the problem with the moving load was discussed. Another problem also with the harmonic force was discussed. Here, moving load is allowed to travel along the breadth of the plate, that is in the y direction. So here, with a constant velocity is moving, and moving load is located at a coordinate x is equal to L. So at any time instant, this is the y coordinate of the load, whereas x coordinate is L. So therefore, the load here, distributed load on the plate, can be expressed with the help of direct delta function. D is the delta is the direct delta function here. This is direct delta. Direct delta function, and then we obtain this for moving load, the generalized forces like that. And again, you can see the generalized force here for the constant moving load, it becomes a harmonic force. It becomes a harmonic force. If this is a constant, say F naught. So generalized force is Qmn equal to F naught sine omega n t, where omega n is the frequency, driving frequency, and it is related to the velocity. The driving frequency. So we can use the steady state formulation that we already used, and we get the expression like that. And the constant Emn and Hmn are determined from the initial conditions. So given the initial condition on the displacement and velocity, actually first we write the complete expression for the displacement. This is homogeneous part, and this is particular integral, and we have here neglected damping. So simplified expression is this. And then given the initial condition here for displacement and velocity, you can see for displacement is W naught, any shape initially at t is equal to 0, and velocity V naught, it is also distributed along x and y. So this distribution is given. And from that, we can again obtain using the orthogonality condition that if you multiply both sides by mode shape function and then integrate it, then sum of the terms that am is equal to r, the term where am is equal to r and n is equal to s will only remain, others will vanish because of orthogonality condition. So in that way, we can obtain this constant Hmn and Emn. So that was discussed in my videos completely with numerical examples. In module 10, we have given some of the approximate methods that is used to obtain the natural frequencies in a continuous system. This is not only restricted to continuous system, but any dynamic system can make use of this approximate method. So sometimes the fundamental frequency, the lowest frequency of a continuous system or any system is accurately or near accurately can be determined using this release method and also by Galerkin method. Finite difference method sometimes gives error, but it requires the finer mesh to get the accurate results. So release method is that it is used for conservative system. And for conservative system, we know that total energy is constant, and therefore we get T max is equal to V max. And from that, we get this frequency omega square equal to V max divided by T star, where you can see that T star is reference kinetic energy. Here you can see the reference kinetic energy that is written here is half UT transpose MU. U is the model vector. This is illustrated with the help of a discrete system, multi-degree freedom. U is a eigenvector. And so you can see here in the reference kinetic energy, there is no omega square terms. Now, when reference kinetic energy is multiplied by omega square, then we get the T max term. Ru, that is the release quotient. You can see this release quotient is V max divided by T star. That is maximum potential energy divided by maximum kinetic energy. And here you can see that omega square is nothing but release quotient. So release quotient is a parameter which is understood as a maximum potential energy divided by the reference kinetic energy, and it is always a positive quantity because it is related to omega square. So we discussed some problems, a cantilever problem we have discussed, and assuming a simple mode shape, say W is equal to Cx square. So that shape satisfies the fixed and boundary condition, but free and boundary condition, that is bending moment boundary condition, is not satisfied. However, this function can be chosen to get an approximate estimate of the frequency, and it gives a simplified procedure to obtain. So we obtain the T max, maximum kinetic energy and maximum potential energy, and then we get the natural frequency of the cantilever beam is 4.47 root over EI divided by ml to the power 4. Now here you can note that actual value is EI by ml to the power 4. That is the system parameters, and it remains constant. And here this constant, the exact value is 3.51 or 5. So there is huge difference, approximately 26% or 27%. So that difference has been reduced by another method that was proposed by Grammar. And he has seen that since the strain energy in the earlier cases was obtained by the derivative process of this mode shape, which was approximate, not an exact mode shape, and derivative process gives more error than the original function. So therefore, he proposed to obtain the strain energy using the bending moment expression. So here, the Grammar proposed that inertial load can be assumed to act on this cantilever beam, and due to this inertial loading, the bending moment at any section can be calculated, and after obtaining the bending moment, one can obtain the maximum kinetic energy due to bending. So in that case, we obtain the maximum potential energy, maximum strain energy due to bending, not kinetic energy. So U max is obtained considering the bending moment expression here, not the derivative process that was used to relate the bending moment in the earlier case. Then after equating to the maximum kinetic energy, the result was improved, and the result was actually 3.53 here, root over EI by ml to the power 4. And actual value is 3.515. So here error you can see 0.43. So this is a very good modification by Grammar. Although the mode shape function, there is no increase of terms, but avoiding the derivative process, it improves the natural frequency estimate. Then there are Galerkin method, that is also an approximate method, but here we require the differential equation. instead of strain energy expression. So the Galerkin method was like that. It was explained in detail. If we assume the mode shape function, say mode shape function is composed of Wx as C1 phi 1 x plus C2 phi 2 x, like that. Okay, up to C3 Cn phi n x. Then it is obtained that if this is also approximate mode shape, but we increase the number of functions, number of terms. Each term again satisfy the boundary condition partially or completely. Okay, if it satisfies completely, then you will get the exact estimate. But if you obtain the frequencies or you obtain the equations to determine the frequency with number of terms, you will get the not only the fundamental frequency but other frequencies. Suppose here only 3 terms are used, so you will get first, second, third natural frequency. Although the first frequency may be accurate, but other frequencies may not be accurate. So here you can see, if you substitute this approximate mode shape to the differential equation, this is the differential equation for the free vibration, maybe a beam or maybe beam bending or maybe axial vibration of rod or maybe torsional vibration of bar, etc. So you will get some error because this is approximate. According to Galerkin, this error multiplied by phi ix. What is phi ix? That is the shape function that is assumed equal to 0. So this equation can be written for n number of terms that we have selected, and we get n number of simultaneous linear equation which can be solved to find the unknown coefficients, and then for non-trivial solution we can set the determinant equal to 0 and we get the number of frequencies. So that is the steps to be followed in Galerkin method, and it is also illustrated in my videos. And one problem that is, you can see the simply supported beam where the mode shape function is, we know that first mode shape is any mode shape in a simply supported beam, first, second, third, whatever may be. It is actually sine function, sine n pi x by L, where n is the mode number. So if we assume the first mode only, then I can write the mode shape is A sine pi x by, it's sine pi x by L. But fortunately, this is the actual mode shape function. So according to Galerkin method, if we substitute this and then carry out the integral, we will get the omega is equal to pi square root over ei by m L to the power 4. So that means if we use the exact mode shape, then we are getting the exact frequencies. Finite difference method was discussed, and with less number of divisions, we get a very crude estimate like that 4.67 ei by m L to the power 4. So that is not correct, and large deviation is there from the exact result. Then module 11, we have discussed 3 items: system subjected to support excitation, response of continuous system to transient excitation, then shock spectrum. So you can see that support excitation, suppose it is elastic, concept is explained with the help of single degree freedom system. So if say a single degree freedom system M, K, C are there, and support is excited, the support is having a displacement y, then but you can see there is no force. So if the support has a displacement y, we can write the differential equation considering the equilibrium of the mass. So if I draw the free body diagram of the mass, you can see that mass is subjected to the force that k into x minus y, that is the relative displacement, the spring force, and the viscous damping force, that is c into x dot minus y dot. This is the mass m. So writing the equilibrium equation, now we can get, this is the differential equation of motion. You can see here that in this case, if I write the equation of motion, it appears that there is no forcing term in the right hand side. The right hand side is 0. So it may mislead that support vibration is a free vibration case, how we get the force. But if you rearrange this, you can see that the forcing term will exist, and it is due to damping and stiffness properties of the system. Here you can see cy dot ky are the force. This is force due to damping, and this is force due to spring. So these forces will act on the mass, and mass will be under the force of this, and the base motion induces these forces. So in the multi-story building also same thing can be interpreted. In the continuous system also, if I see a cantilever beam whose base is having a displacement, say a constant displacement ys, which is varying with time, or in any other manner, it is not, it may not be constant, it may be harmonic motion or any other motion. Then we can write the total displacement of the beam will be support motion plus the elastic deformation of the beam. So now this is the beam equation, because there is no force actually acting here on the beam. So in the first step, we can write that the equation of the motion of the beam is like a free vibration equation. But when you substitute is y equal to ys plus yb, and then rearrange this, you will find that the right hand side contains two terms, minus c y dot s minus m double dot ys. So these are the forcing function for the beam when the support has a displacement. And yb is the displacement of the beam, that is the elastic deformation of the beam. Total displacement, of course, has to be found after adding the base motion. Then the application of support motion, that in practical field, we find that transmittivity ratio for the displacement that is obtained, and it is the formula that is derived for single degree freedom system. But basic definition of transmittivity ratio is absolute displacement of the mass divided by absolute base displacement. Now, it is example is given with the help of cantilever from the basic definition from the first principle. So the base is having a harmonic motion, and other parameters are given. So we have found that the equation of motion taking in an approximate mode shape, and considering the mode superposition is valid, only first mode we have taken, and then we have found this. The equation of motion is this, neglecting damping. So it is a harmonic motion that you can see here, and frequency ratio here in this case, you can see that this is the natural frequency, driving frequency ratio is found, and the steady state amplitude is this. So at the phi and steady state amplitude is found this. So total displacement of the beam at the phi m, this is the base displacement amplitude plus this is due to steady state motion of the beam. So total is becoming 0.036 meter. And this total displacement divided by the base displacement, that is 0.01, gives the transmissibility ratio. That is here it is 3.6. It is worked out. So one interesting thing you can see that if you plot the frequency ratio, that omega by omega n, that is the driving frequency divided by natural frequency, and the ratio, transmissibility ratio x by y, then you will get a plot like that. This is for very low damping. And as the damping increases, you can see the curve become the flatter and flatter. And ultimately, you can see here this it will further flatten. And one interesting thing you can see that all the curves here passes through a common point, that is frequency ratio √2. So, and frequency ratio greater than √2, you will find transmissibility ratio is less than 1. So for motion reduction, we require omega by omega greater than √2, which means that natural frequency of the system should be less than 0.707 omega, that is 1 by √2 omega. Then we have discussed shock spectrum for different excitation, half sine pulse, rectangular pulse, step force with finite rise. Okay, so this is the, what is response spectrum? Response spectrum is the maximum displacement of a single degree freedom system with different time periods. That is it is a plot of maximum displacement or maximum velocity or maximum acceleration of a single degree freedom system against the different time periods. So here the Tn is the time period of the system and Tt is the duration of the pulse, because this is the shock spectrum that is obtained for the sine pulse. Sine pulse having a duration Td, rectangular pulse have a duration Td, and it has also different type of spectra. And step force with finite rise, this is the important parameter, the Tr, that is the rise time. So here the shock spectrum for half sine pulse is shown. That is the overall maximum response. And with the help of this curve, we can find what will be the peak displacement at a particular ratio of Td by Tn. Similarly, step force with finite rise, that is here shown. You can see that one important thing, that Tr less than Tn by 4. Tr by Tn is less than 0.25. Okay, you can see it is approximately 2. So that is 2 times the static displacement. RD is nothing but a ratio of maximum dynamic displacement to the static displacement. It is the non-dimensional parameter. So here you get, this is approximately 2. That is also true for this this step force, constant force. That means when Tr becomes very small, this force resembles the constant force that is acting on this system. Then in module 12, we have discussed the Duhamel integral, numerical evaluation of the Duhamel integral and direct integration scheme, and then spectral analysis for earthquake motion. So we have discussed this Duhamel integral is this, and then after decomposing it, we find that it can be written like that, where AT and BT are the integrals that can be obtained. So if f tau and f tau here is not an ordinary function that can be integrated, is a very complicated one, then we can use the numerical technique for integration and we can find the response numerical. Recursive relationship also given in the modules. Direct integration methods was discussed. Central difference method was first discussed. That is, the derivatives are written in finite difference form. And ultimately, that knowing the force displacement at previous time steps, I and I minus 1, we can determine the displacement at the current time step. I is the previous time step, say I plus 1 is the current time step, and 2 previous time step is I and I minus 1. So we get this. So this represents that it is like a effective stiffness. So we can represent this equation. Commonly it is written K effective, K cap is the K effective, and Ui plus 1 equal to P effective. So this represents a static case. Say K delta equal to P, that we know. And from that we can find out the displacement and then velocity, etc. But the finite difference method involves error because of we are writing in a difference form, and when the derivative process is involved, the error becomes large. The condition for stability is given delta t by Tn root over E is less than 1 by pi. It's sometimes useful, but usually delta t should be less than 0.1 Tn. Sometimes even you can lower this delta t depending on the time period of the structure. Then Newmark method is called. Here Newmark sometimes in some author prefers to tell it Newmark beta method because here beta is a parameter which plays a significant role in the numerical integration. So there are two methods. One is average acceleration method and linear acceleration method. Between two time steps, small time steps, Ti and Ti plus 1, we assume that the average acceleration, that is acceleration is constant and it is average of the acceleration at the time step I and I plus 1. Then in linear acceleration method, we assume that the acceleration varies linearly, and we can find that any time instant measured from this Ti, the acceleration expression is this. So Newmark has given this expression for this displacement and velocity, and we can express this in the incremental form after certain manipulation. Here also you can see that incremental deflection is equal to K inverse del P cap. Del P is the incremental effective load. Effective stiffness is defined as this parameter, where gamma and beta plays an important role in this process. Gamma and beta are different for different methods. Say for average acceleration method, gamma is 0.5, beta is 0.25. Whereas linear acceleration method, gamma is 0.5, beta is 1 by 6. So we can find this effective load for any method, average acceleration or linear acceleration method. Then you can also find the effective load knowing the displacement and velocity. Displacement and velocity at the time step I. Now here the this acceleration is given, but from the information of displacement and velocity, the acceleration can be determined that acceleration can be determined like that. Ui double dot equal to m inverse, there is 1 by m for a single degree freedom system. And if this is a Pi, the force minus C Ui dot minus K Ui. So from this equation, once this is given, the displacement and velocity, Ui and this is given ui and ui dot. It implies that u dot I double dot I can also be obtained from this equation of equilibrium. Stability of Newmark method is better than the central difference method, and we have seen for stability, especially for this average acceleration method, that shows that delta t by tn this less than equal to infinity. That indicates that it is stable for any finite value of delta t, but it is not true. Okay, so delta t should be taken small. In linear acceleration method, gamma is 0.5, beta is 1.6. If it so, then delta t by tn becomes less than equal to 0.55. Newmark's method is implicit method, whereas the central difference method is explicit method. Then we have spectral analysis. The basic thing of spectral analysis is that instead of forcing function, the spectral density of the excitation, whether it is earthquake, wind, or any other excitation, must be known. So different spectral density curve for the excitations are given, and from which we can obtain the spectral density of the response X. SF omega represents the spectral density of the forcing function, and this is the spectral density of the response quantities, and it is related to h omega square, where h omega is the complex frequency response function. And one important thing is that when the spectral density function is integrated over the frequency range of interest, say omega 1, omega 2, we get the mean square value of the x. So sigma x square, that is the variance or mean square value. If the mean is 0, we can obtain like that. So there are some questions for the live session that I have obtained. So how is the generalized force? I've written here question because question I've got on yesterday. How is the generalized force with moving load determined in the plate? So that I've discussed, the moving load on the plate and beam having this similar type of effects, that it is position is changing with time because it is moving with certain velocity. Although here we are taking the constant velocity. So therefore this is expressed as P into direct delta x minus L. The direct delta function has to be used. So two direct delta function is used here because it is specified at x is equal to L, and this is also changing with time with velocity. Integration of direct delta function, that is any function that you multiply. Any function if you multiply, say phi xy, then if you have direct delta function y minus b, that any function multiplied by the direct delta function, and that then it is integrated, say double integral between any limit minus infinity to plus infinity. The value of the integral will be simply the function evaluated at the points where the direct delta function is defined. So phi, it is defined at x is equal to a and y is equal to b. So value of the integral will be like that. So this is used to evaluate this generalized force in the case of plate with the moving load with the help of integration using direct delta function. Here double integration is involved. The second question is, which one is the numerical method for continuous system? A numerical method that I discussed here is illustrated with single degree freedom set, that is a discrete system. Multi-degree freedom also can be extended. But for continuous system, The generalized coordinate equation is obtained using the model superposition technique and orthogonality condition. After that, it resembles the same equation as in case of single degree freedom system. So this direct integration scheme that I have discussed developed for ordinary differential equation, but after decomposing this into generalized coordinates, ordinary differential equation with generalized coordinates, we can apply the numerical methods, that is whatever we discussed here, to obtain the response and then combine again with the mode shift to get the response at different locations. So that is the procedure with continuous system. Then another question is why two subscripts are given in natural frequency of the plate. Now plate bends in different half waves that is formed in the x and y direction. Suppose a rectangular plate at a particular frequency it is bending like that, in another direction it is bending like that. Okay, so number of half waves are different. Here number of half waves are 2 and here it is 3. Say this is the x direction and this is y direction. Here number of half waves in the x direction is 2, but you can see here number of half waves in y direction n is equal to 3. So here the natural frequency omega 23. So therefore, to indicate the number of half waves formed in a particular mode in x and y direction, two subscripts are used in the natural frequency expression. The fundamental frequency, of course, is given when the lowest number of half waves, that is one half wave, is formed in both x and y direction. So omega 11 is the fundamental frequency. So that for plate, it is always meaningful to attach two subscripts for the frequency. How the response spectrum curve for single degree freedom system can be used for continuous system. That also has a similar reply, that first you decompose the partial differential equation into ordinary differential equation in generalized coordinate, and then use the response spectrum curve, because response spectrum curve is developed for single degree freedom system. So once you get this single degree freedom equation, then read the response spectrum curve against the time period and obtain this ordinates, the response spectrum ordinate. If you consider only first mode, then only you take this coordinate according to time period of the first mode. But if you consider other modes also, then similarly obtain and then sum up all these coordinates, peak response multiplied by the mode shift function at a particular location. Like that you will get. There are some questions on the discussion forum that I have already explained, and also I have given the reply, but for your convenience I have written here. Further explanation is required, I can answer, I can discuss this. So one question was there, the support excitation, it is confusing actually whether there is any force or not. The support is having displacement, but how the force vibration part comes, that I have discussed, because the relative motion between the support and the structure induces the force on the system because of damping and inertia properties. And in case of single degree freedom system, this you have seen that stiffness is also coming into picture. So apparently it shows there is no force, but due to this inertia and damping properties, or the stiffness and damping that is there in a discrete single degree freedom system, the force will be induced in this structure. So that is the case, and we have to obtain the force vibration response The forcing term contains this velocity of the support motion and acceleration of the support excitation, or the velocity of the support motion and displacement of the support motion. Then another thing is the modal participation factor. Is it the same as mass participation factor? It is almost same here in this earthquake analysis that was discussed in the different course of practice. In our basic definition, we have written the mode participation factor is eta double dot k plus omega k square eta k equal to capital gamma, that is the modal participation factor ft. So this is modal participation factor. It is defined as the ratio of two integrals m phi k x dx divided by m phi k square x dx. You can see this is the integral that is written for the continuous system. If we write it for a discrete system, instead of integral, the summation will appear. So this is the procedure or formula that is given in the course of practice for earthquake excitation in spectrum analysis using mass participation factor. Modal participation factor actually indicates the amount of contribution, that is the contribution that is made by a particular mode. So in the kth mode, what is the contribution in the generalized force and what is the influence in the response? And where mass participation is used, because you can see this m is there in both numerator and denominator. Here it is a m that is a constant throughout, but in a discrete system, a multi-degree freedom system, different floats have different masses. So the summation will indicate m1 phi 1 plus m2 phi 2, but this will be in a vector form. Okay, because the eigenvalues and eigenvectors when arranged, it will give a model matrix, and you can accordingly write the modal participation factor in the summation terms. So that is indicated in the course of practice for earthquake resistant design. Regarding the response of step with a finite rise time, here the question was that it is a matter of this constant force after time tr. That is, the force was like that. Force was like that. First it was rising here, then it remains constant. Okay. So rising time is tr, and this is ft, and here t. So after that, force remain constant, say p. But oscillating term is there in the form of cosine function. This is due to fact that we have obtained this forcing part, that is the particular integral using the Duhamel's integral. So this is the Duhamel's integral. That is called particular integral that we found. Now here you can see that ht is the impulse response function. This is the impulse response function. And this contains a sine term, sine function. So therefore, when we integrate a sine function, because f tau is constant here, okay. So constant will come outside the integral, but when the sine omega nt will be integrated, obviously this cosine term will come. So therefore, cosine function comes in the picture. So this is the questions I have received in the live session and discussion forum. So I have answered. If any further queries are there, you can pose the questions, and even you can discuss now. There is no question. There is no question. So we have completed the live session. And now I think you are fully equipped with this different topics, and best of luck for the exam. Okay. Thank you.